Let's start chapter 4, continuous time signal analysis, the Fourier transform. In chapter 3, we succeeded in representing periodic signals as the sum of sinusoids or exponentials. In this chapter, we will extend this spectral representation to aperiodic signals. First, let's revisit the concept of periodic signals and aperiodic signals. So based on the definition, we know periodic signals will repeat itself with a fundamental period. For example, like the signals here and the signals here. In practice, we can never tell whether an observed signal is truly period or not, only based on a window of finite time. Therefore, signals in practice are treated as aperiodic with only finite support. We mean finite support that signals, the values of the signal are non-zero only over a finite time interval. For example, a signal like this, signal xt, and a signal here, signal xt. We know the Fourier analysis can be applied to periodic signals. So therefore, we want to construct periodic signals using aperiodic signals. I will show you two examples. So for example, let's look at this signal xt at the left-hand side. Xt is an aperiodic signal. Now let's select a time interval t0. Let's call it t0. Let's make this t0 long enough so that when we extend xt to the left-hand side and right-hand side, the signals will not have overlaps. So for example, if we choose so that t0 is like this, then when we extend this signal to the left-hand side and right-hand side, then we have a periodic signal, xt0t. The fundamental period is t0. Now think of this process. If we let t0 to become larger and larger, the signals on the left-hand side will push towards the negative infinity, and the signals on the right-hand side will push towards the positive infinity. Then you can think of the extreme case. When t approaches infinity, then the pulse, the signal between negative t0 over t and t0 over t will repeat after an infinite interval. In this case, we can think that xt0t, when t0 is infinity, it will be exactly same with xt. Let's see another example. Let's look at the signals on the right-hand side. xpt is a periodic signal. The fundamental period is t. Now let's do one thing. Okay, let's fix the height of the pulse to a. Let's fix the pulse to a and fix the duration, the width to tau. Okay? So tau is fixed. Okay. Then now let's increase the fundamental period of t. If we do that, when this capital T becomes larger and larger, this rectangular pulse will push away and towards the positive infinity. When the capital T approaches infinity, then we will see this periodic signal will just looks like xt. Therefore, we can have the conclusion any aperiodic signal can be defined as a periodic signal with an infinite time period. This is a very useful definition that makes it possible to use Fourier analysis to aperiodic signal. Now we know that x capital T0 t is a periodic signal. So therefore, we can apply Fourier analysis to the periodic signal xt0t. Also, we know that when t0 approaches infinity, xt0t is exactly the signal xt. Now let's use Fourier series to represent xt0. The exponential Fourier series of x capital T0t is dn exponential jn omega 0t, and from negative infinity to positive infinity. Omega 0 is called the fundamental frequency. It's defined as 2 pi over T0. So T0 is the fundamental period. Dn is a coefficient. It's calculated in this way. This is 1 over capital T0 integration from negative T0 over 2 to positive T0 over 2 xt0t exponential negative j n omega 0t dt. Observe that the integration of xt0 between negative T0 2 and T0 over 2 is the same as integrating xt over negative infinity to positive infinity. The integration is exactly the same. So therefore, the dn can be expressed in this way. It's 1 over T0, the integration from negative infinity to positive infinity, xt. So xt is the aperiodic signal, the exponential j n omega 0t dt. Again, we know when T0 approach infinity, xt0 will be the same with xt. It's interesting to see how the nature of the spectrum changes as t increases. To understand this behavior, let's define a new function, x omega. X omega is defined in this way. From the integration is from negative infinity to positive infinity. The signal xt is the aperiodic signal times exponential negative j omega t dt. Notice that this integration is with respect to t. Therefore, it is a continuous function of the variable omega. So omega is defined as the frequency. We know this Fourier coefficient is defined in this way. It's 1 over T0 integration from negative infinity to positive infinity xt exponential negative jn omega 0 t dt. When we compare this integration with this defined function, then we notice that this part, it is just the value of x omega when omega is n omega 0 t. Therefore, the Fourier coefficients can be expressed in this way. So dn will be 1 over dt x n omega 0. Now, let the t0 approach infinity. So we let the t0 approach infinity in a special way by doubling t0 each time and then repeatedly doubling t0, then t0 will approach infinity. Based on this definition, okay, then we know that dn is just the sample of the function we define x omega times 1 over t0. This sampling is uniformly at the interval omega 0. Sample is at 0, omega 0, negative omega 0, 2 times omega 0, negative 2 times omega 0. Based on the definition of the fundamental frequency, when we double t0, we know it halves omega 0. Therefore, there are now twice as many of the sampling of the components in the spectrum. However, when we double t0, the envelope, so 1 t0 x omega is also half. If we continue this process repeatedly, the spectrum becomes denser, while its magnitude becomes smaller. This is the Fourier. This is the Fourier series representation of the periodic signal xt0t. We know the coefficient, so dn is 1 over t0 xn omega 0. Now let's substitute the Fourier series representation of xt0, the coefficient, with 1 over t xn omega 0. After substitution, we have xt0t is the sum of n from negative infinity to positive infinity, xn omega 0, t0, exponential jn omega 0 t. We know as t0 approaching infinity, the fundamental frequency omega 0 will approach 0. Therefore, it's better to replace omega 0 by a more appropriate notation. Let's use delta omega to represent a very small omega 0. If we replace omega 0 with delta omega 0, we have x t0 t, the sum, and from negative infinity, positive infinity, x and delta omega. Then the t0 based on the definition, so omega 0 is equal to 2 pi over t0. So therefore, t0 is equal to 2 pi divided by omega 0. So if we replace t0 by 2 pi omega 0, so therefore it will be, again, when we replace omega 0 by delta omega 0, it will be delta omega 0 over 2 pi times exponential jn delta omega t. This equation shows that xt0t can be expressed as a sum of everlasting exponentials at frequencies 0, delta omega plus and minus, plus and minus 2 times delta omega plus 3 times delta omega and continue. So this is exactly the Fourier series. Then the amount of frequency and delta omega, the amount of frequency and delta omega, it will be x and delta omega divided by 2 pi. The sum on the right-hand side can also be considered as the area under the function x omega exponential j omega t. Then when delta omega becomes very small and approaches to 0, this infinite sum will become the integration. To be 1 over 2 pi integration from integration of delta omega will be changed to d omega. So x and delta omega will be x omega, then exponential j omega t d omega. This is called the Fourier integration. To recapitulate, x omega is the direct Fourier transform of xt. It's defined as x omega is equal to integration from positive infinity, negative infinity to positive infinity, xt times exponential negative j omega t dt. Symbolically, we can write it in this way: x omega is equal to f. F represents Fourier transform. Xt is the inverse Fourier transform of x omega. Xt is defined in this way: 1 over 2 pi integration from negative infinity to positive infinity x omega exponential j omega t d omega. Symbolically, we can write xt is equal to the inverse Fourier transform of x omega. It is helpful to keep in mind that the Fourier integral is of the nature of a Fourier series with fundamental frequency that omega approaching 0. Therefore, most of the properties of Fourier series can be applied to the Fourier transform. The transform x omega is a frequency domain specification of xt. X omega is complex, so therefore we can write it in the polar form. The absolute value of x omega is the amplitude, and this is the angle, is also called the phase.